All right, so our next speaker is Daniel Gabric from the University of Waterloo.
Hi. So this is about words that almost commute, and so first let's talk about words that commute first. So when does xy equal yx for non-empty words xy? Well, Lyndon and Schützenberger gave necessary and sufficient conditions for when x and y commute. So their result is that if let x and y be non-empty words, then xy equals yx if and only if there exists a non-empty word z and positive integers ij such that x equals z to the I and y equals z to the j. So a word w is a power if w is 0 to the I for some non-empty word u and some integer I greater than or equals 2. Otherwise, w is said to be primitive. So if you go back to the theorem of Lyndon-Schützenberger, we see that two words, x and y, commute if and only if xy and yx are powers of the same word. So if we use this, we can use this characterization, and if we have a formula as well for the number of length and powers, then one can count the number of pairs of words xy with the length of xy being n and xy commuting. So Fine and Wilf later showed that one can achieve the forward implication of the theorem of Lyndon and Schützenberger with a weaker hypothesis. So this is the following result they gave. So if we let x and y be non-empty words of lengths m and n, then if xy and yx agree on a prefix of length m plus n minus gcd of mn, where gcd is the greatest common divisor, then we have that x and y commute. So they showed that this result was optimal by constructing words of x and y of lengths m and n such that they agree on this length m plus n minus gcd of m and n minus 1 prefix, and they differ right after that prefix. And these pairs of words actually almost commute. So if you have a pair of these words, then that satisfy this condition that xy and yx agree on the first m plus n minus gcd mn minus 1 positions, but disagree on the position right after, then xy and yx differ in exactly 2 positions. So on the Hamming distance. So the Hamming distance between two equal length words is just defined to be the number of positions where they differ. So we said before that these Fine and Wilf pairs of words, they almost commute. And they almost commute because xy and yx differ in exactly 2 positions. Now, when the Hamming distance between xy and yx is 0, well, that's just xy and x and y commuting. Now, one might think that the next smallest Hamming distance that xy and yx can take on is 1, but that's not true. It's actually 2. So, and that's by a result that was proved by Geoffrey Shalit. And here's the theorem. So it shows that xy and yx, the Hamming distance between them can't ever be 1. So the proof is actually quite simple. So suppose by contradiction that the Hamming distance is in fact 1. Well, then that means that xy and yx differ in exactly 1 position. So that means we can write xy equals uav and yx equals ubv, where a and b are distinct symbols. But then this would mean that xy and yx have different numbers of a's and b's, which is impossible. So if the Hamming distance between xy and yx is 2, then we say that x and y almost commute. And also, the words xy and yx are also said to be conjugates. So when we're talking about pairs of words, x, y, that almost commute, we can also equivalently talk about words u that have a conjugate v such that the Hamming distance between them is 2. Just an alternate way of talking about the same thing. So can we characterize almost commuting pairs of words in a similar way that Lyndon and Schützenberger characterized commuting pairs of words? And also, can we count the number of almost commuting pairs of words? In this talk, we'll answer these questions, and we're going to answer these questions using the conjugate formulation of the problem. So here's a brief outline of some of the results that we'll go through. So we'll give a characterization of words that have a conjugate such that the Hamming distance between them is 2. We'll give a characterization of words that have exactly one conjugate such that the Hamming distance between them is 2. A characterization of Lyndon words that have a conjugate such that the Hamming distance between them is 2. We'll give formulas for these quantities, and at the end, we'll go through some asymptotic behavior of some of these quantities as well. So before we get into the details of the results, we need some notation. So all of the following definitions are assumed to be over a k-letter alphabet, here from 0 to k-1. And we let sigma be the left shift map, and we're defining this so that we can talk about specific conjugates of words. So we can talk about, the ith conjugate of a word or something. We let big H of n denote the set of all length n words u that have a conjugate v such that the Hamming distance between u and v is 2. We let little h of n denote the number of such words. We let big H n I denote the set of all length n words u such that the Hamming distance between u and the ith conjugate of u is 2. And then we let little h n I denote the number of such words. So here's a useful property that we're going to use later. So if we have a length n word u and an integer between 1 and n-1, then we have that if u is in h of ni, then u is also in h of n-i. So first suppose that I is less than or equal to n over 2. It's less than or equal to half the length of the string. Well, then we can write u as xtz, where x and z are of length I. And we also know that since u is in hni, then when we take the Hamming distance between xtz and tzx, we have to get 2. But we can also split this Hamming distance up because we know that xt is the same length as tz, and z is the same length as x. So the Hamming distance, the total Hamming distance here, is equal to the Hamming distance of xt and tz plus the Hamming distance of z and x. Now we consider another word, zxt, which is clearly a conjugate of xtz. All we have to do is just rotate the xt around. And now we have this Hamming distance between xtz and zxt. And we can split up the Hamming distance in the same way that we split up the previous one. We have we can split it up as the sum of the Hamming distance between x and z and the Hamming distance of tz and xt. And we already know that this evaluates to 2, so this Hamming distance evaluates to 2. And we also know here that since we're rotating this xt, and xt is of length n-i, that means that u is in hn n-i. And basically the same argument works for when I is greater than n over 2, but now we're splitting up u into z to y, where z and y are of length n-i instead of I. And then it's basically the same procedure. And so this lemma, it implies that hni is equal to hn n-i, because you can just, the forward implication, you can just substitute n-i for I, and then you get if u is in hn n-i, it's also in hni. So you have both directions. So now we're ready to characterize HNI. So let n and I be positive integers such that n is greater than I. Let G be the greatest common divisor between n and I, and let W be a length n word. And now we're going to split up W into length G blocks, where each xj, so we're splitting it up into x0, x1, x2, each xj is of length G. Then W is in HNI if and only if there exist two distinct integers, J1 and J2, such that the Hamming distance between xj1 and xj2 is 1, and xj is equal to xj plus I over g mod n over g for all j that are meaningful and not equal to j1 or j2. So we'll show the forward direction here. First, suppose that W is in HNI, and we write W in the same way where we split up W into length G blocks. And now we know that W is in HNI, so we have the Hamming distance between W and the ith conjugate of W is 2. And also, since W is split up into length G blocks, where G is the greatest common divisor of n and I, and G divides I, all we need to do to rotate this set of blocks is just take the first I over G blocks and rotate them to the end. And we get that in this Hamming distance, if we look at W, each index of the x parts, so 0 to n over g minus 1, it maps, so each index j maps and gets compared to xj plus I over g mod n over g. So we can rewrite this whole Hamming distance as just the sum from going from j equals 0 to n over g minus 1 of the Hamming distance between xj and xj plus I over g mod n over g. And since W is in HNI, we know that this evaluates to 2. Now, in order for this to be 2, in order for this sum to evaluate to 2, one of the following must be true. We either must have that there exists a single j such that the Hamming distance between xj and xj plus I over g mod n over g is equal to 2, and then all of the other Hamming distances would evaluate to 0. Or there exist two distinct integers, j1 and j2, such that the Hamming distance between xj1 and xj1 plus I over g mod n over g is 1, and then the same thing for xj2. And first, let's assume that the first is true. So assume that there exists one j such that the Hamming distance between xj and xj plus I over g mod n over g is 2. Well, like I said before, that would then mean in order for this sum to evaluate to 2, all the other parts of the sum would have to give 0 contribution. So the Hamming distance of all of those must be 0. We also know that the additive order of I over g modulo n over g is just n over g. So if we start at some integer between 0 and n over g minus 1, and we keep adding I over j and we mod n over g every time, then we'll get back to the original integer after n over g steps. So we have that since all of the Hamming distances other than this j and j plus I over g mod n over g are equal, so we have this chain of equality going from j plus I over g mod n over g, j plus 2I over g, etc., all the way to xj. So we have that x sub j is equal to x sub j plus I over g mod n over g. But we also assumed that the Hamming distance between those two is 2. and that's a contradiction. So this case cannot be true. So that means that now suppose that there are two distinct, so that the case 2 is correct. So suppose there are two distinct integers such that the Hamming distance between xj1 and xj1 plus I over g mod n over g is 1, and the same thing is true for xj2. Well, the same thing is true about the additive order of I over g modulo n over g, and we can get the following. So we have this chain of equality between j plus, or j1 plus I over g mod n over g all the way to xj2, and the same thing is true for xj2 plus I over g mod n over g. And therefore we have that the Hamming distance xj1, xj2 is equal to 1. And the other direction is easy to prove, so I won't go through that. So now that we have this characterization, we can count the number of words in HNI. All we need to do, so we need to specify, we need to count the number of ways to choose J1 and J2, and we also need to choose the number of ways to, or the number of ways to choose xj1 and xj2. So J1 can go from 0 to J2 minus 1. J2 can go from 1 to n over g minus 1. Therefore, there are a half times n over g times n over g minus 1 choices for J1 and J2. There are k to the g choices for xj1. And now we know that xj1 and xj2 differ in exactly one position. So given that, there are n times k minus 1 choices for xj2. And now we just multiply all of these together and we get the following theorem, which is a formula for the number for little HNI, for the number of words in big HNI. So now we can try to count big H of n. And so back to one of the properties we proved in the beginning, we have that HNI equals HN n minus I. And so this means that we only really need to concern ourselves with HNI for I less than or equal to n over 2. And we also know, so clearly that HN is less than or equal to the sum of HNI from 1 to the floor of n over 2. But in this sum, we are double counting a lot of words that are in multiple HNI. So we need a way to figure out which words, characterize which words are in multiple HNI. And so we need a theorem similar to the Fine-Wilf theorem, which tells you about when words have multiple periods and characterizes those words. We need a similar characterization for these words in multiple HNIs. So here is this result. Let nij be positive integers such that n is greater than or equal to 2i, and that's greater than 2j. And let g be the greatest common divisor between n, I, and j. And let w be a length n word. Then w is in HNI and HNJ if and only if there exists a length g word u, a length g word v, such that the Hamming distance between u and v is 1, and we have a non-negative integer p that's less than n over g, such that w is equal to u to the p v, u to the n over g minus p minus 1. So this lemma implies basically that a word is in multiple HNI if it is Hamming distance 1 away from a power. And not just any power, it has to be a power of exponent 4 or greater, since we see that, so the greatest common divisor between n and I, since n is greater than or equal to 2i, is n over 2, and then j, we're bringing a j into the mix, and j is less than I, so then we have to have that the greatest common divisor between n, I, and j is less than or equal to n over 4, and that would lead to the exponent of 4 or greater. So now let P sub k of n denote the number of length n powers, And from that last, from the formula of h and I and the former characterization, we get the following theorem. So let n be a positive integer, then h of n is equal to this sum from 1 to the floor of n over 2 of h n I minus h prime of ni, where h prime of ni is defined as the following. And this h n I, it's just all those words that are in h n I, but also in some other h n j for j less than I. So now we counted the words in hn and hni, but what about the number of length n words that have exactly one conjugate such that the Hamming distance between them is 2? Let w be such a word. Well, we know that hni is equal to hm n minus I, so we have to have that I is equal to n over 2. If I was anything else, then we would have at least 2 conjugates that that lead to this Hamming distance being 2. And also, w cannot be in any hnj for j less than n over 2 for the same exact reason. There would be at least 2 conjugates. So therefore, it leads to the following theorem. If n is odd, then there are no length n words with exactly one conjugate, such that the Hamming distance between them is 2. And if n is even, then there are hn n over 2 minus n times k minus 1 times p of k n over 2 length n words, such that exactly one of its conjugates has Hamming distance 2 away from it. So now on to Lyndon conjugates. Lyndon word, or a word is said to be a Lyndon word if it is strictly smaller than all of its non-trivial conjugates. And fact here, all Lyndon words are primitive. And here's the result. There are h to the n over n length n Lyndon words u that have a conjugate v such that the Hamming distance between u and v is 2. And so to see this, we have that, well, if we have w and w's I conjugate and we know what their Hamming distance is, well, that Hamming distance is preserved if we shift w and sigma iw by the same amount. The characters that are being compared are preserved. So that means that if w is in hn, then any conjugate of w is also in hn. So all that it's left to prove then is that every element of h of n is primitive. Suppose otherwise. Suppose that there is a power in h of n. Well, then w equals u to the m for some non-empty word u and some m greater than or equal to 2. And any conjugate of w is of the form ts to the m, where u equals st. So let w prime equals ts to the m, and it's a conjugate of w. Now we have this Hamming distance between w and w prime. And we know that st and ts are of the same length, and they're repeated m times. So the Hamming distance between w and w prime is then just m times the Hamming distance of st and ts. But we know that the Hamming distance between st and ts can either be 0 or greater than or equal to 2. It can't be 1. So what does this imply? Well, if it's 0, then the Hamming distance between w and w prime is 0, since m times 0 is 0. If it's greater than or equal to 2, well, then the Hamming distance between w and w prime is greater than or equal to 4, since m is greater than or equal to 2. In either case, the Hamming distance isn't equal to 2, and that's a contradiction. So here's some asymptotic behavior of h of n. And when n is a prime number, we have that it behaves like a polynomial. It's equal to this polynomial over here. And this is actually pretty easy to show. Since the greatest common divisor between n and I is 1, for all I between 1 or 2 and n over 2, then it's pretty easy to simplify the sum you get from h of n, because all of the GCD ni's simplify to 1, and you're just simplifying a bunch of the sum of polynomials. Also, when n is so if we let n be a positive integer, then when n is even, so h of 2n is greater than or equal to a half n times k to the n. So when it's even, we have that the number of such words is bounded below by an exponential. And this is also pretty easy to see. We see that h of 2n is a subset of h2n. Therefore, h of 2n is greater than or equal to h of 2n n. And then we get that it's greater than or equal to 1/2 n times k to the n. And so this shows that h of n behaves like a polynomial for infinitely many n and as an exponential for infinitely many n. And also shows that there's no one easily expressible bound on h of n. So in this talk, we characterized and we counted all length n words that have a conjugate such that the Hamming distance between them is 2. And this formula corresponds to the following OEIS sequence. There's a link to it here. And also one can use this formula to count the number of pairs of almost commuting words such that the length of xy is fixed. We characterized and counted all words with exactly one conjugate such that the Hamming distance between them is 2. And that also corresponds to the following formula in OEIS. We characterized and counted all Lyndon words with exactly one conjugate such that the Hamming distance between them is 2. And this also has a formula in the OEIS, or this has a sequence in the OEIS. And finally, we showed that there is no one easily expressible bound for h of n by showing that h of n behaves as a polynomial for all prime n and that h of n behaves as an exponential for all even n. And yeah, okay, that concludes the talk.
Thanks, Daniel. Are there any questions? Stefan.
Yeah, hi Daniel. My question would be whether you think that there is a relation between these almost commuting words and Fine-Wilf words, which are extreme also in the sense that, you know, if you add, they have 2 periods, and if they're as long as possible, having 2 periods and not having the GCD, so it's somehow, you know, it could be related because when you add this last letter, it will cause a period. So I wonder whether you see any relation.
Which words are these? I didn't hear what words you were talking about.
These are called Fine-Wilf words.
Oh yeah,
they are the longest words which have 2 periods but don't have the GCD.
Yeah. So yeah, actually, those words they are also almost commuting. So
yeah, okay. So these are the special case.
Yeah, they're a special case. They're not they're a special subset of almost commuting words. Yeah.
A big part, do you know?
No, I don't think they're a big part.
Mm-hmm. Okay. Thank you.